Hi, everybody. Let's talk about running networking labs with Docker user experience. Since I'm new to NLNOG and to the Netherlands, let me introduce myself. Hi, I'm Roman. I'm a systems engineer with Nokia, and I work primarily on things that have to do with model-driven network automation. I do love open source communities which are built around networking, and I do contribute to them. If you want to talk to me, reach out either through LinkedIn or I'm quite active on Twitter, and this is my Twitter handle. Since we are short on time, let me just jump over to the first meaningful slide, which is how do we run networking labs today? Because we do love to run labs, right? That's the only way we can blame the vendor, for instance. And there is one thing that is kind of an elephant in the room. The network emulation software projects like EVE-NG, GNS3, and a few smaller others, they are purposely built for that. They are proven. They've been running in our labs for decades, and we know how they work. They are quite free and available to download to everybody. Some premium features of EVE-NG might require some extra bucks, but yeah, for the most of the part, it's really free. They have a nice UI, right? We can drag and drop our elements on the pane, we can interconnect them with links, and that's our topology. That's really great, useful, and human-friendly. On the flip side, what I think these tools kind of lack of is that they have a very VM-centric approach. That means that inherently they have weak container support. I will talk later about why I think container support is really important here. But yeah, that we will leave for later. They are also quite heavy, and everybody knows that it's a burden to install EVE-NG or GNS3. You need either to have a bare metal server or you need to have a VM, and these will be allocated for the long period of time. You cannot bring this environment up and destroy it after. It will be there with you for a while. Also, what was previously a plus, the UI thing, it might be considered a minus, because if you are on the development side or on the testing side, you might be more comfortable with textual-based configs, like YAML configs or TOML or whatever you have. You might be just looking at this as the artifact that you would like to type in and not drag and drop and click around. In the other bucket, there are tools like OpenStack or Proxmox with the VM orchestrators. You might want to use them to create networking labs, and they are quite popular. They're in numbers in medium and large enterprises. They are there. The problem with these tools, though, is that to run networking labs specifically on those projects, it requires quite a lot of integrational effort. You need to know how tools work, how to interact with the objects that they expose, et cetera, et cetera. They are, of course, VM-centric as well because they are VM orchestrators, meaning that there are problems to run containers on them in a way so you can use them in the networking labs. Sometimes even to get a clean data path might be challenging with these tools because if your data path has a breach, a typical Linux breach, then you might have problems with LECP or slow protocols, and sometimes even with LLDP. There is no UI nor CLI that is really tailored to networking labs. They do have UI and CLI for the project themselves, but these elements are really for the constructs of the OpenStack or Proxmox, like create a VM, create subnet, create a router, but not create a network topology. And on the far end of the spectrum, there are custom automation solutions. Everybody have them, like a crazy bash scripts with thousands of lines that spin up libvirt VMs or create Docker containers, and they might be really a silver bullet for you. They can solve all the problems that you might have. The only downside is that they are tailored only for you. So if you want to take your custom solution and take it to your customer or to your partner or to your peer, they might not be able to run it at all because you took some decisions that are really specific for your environment and they will not fly in their environment. And now to the point where I mentioned that the weak container support is kind of important. Why do we do that? What do we gain by moving away from VMs when we talk about network labs? Well, first, of course, we will gain containerized network operating system support. And if you think that there are no containerized network operating systems, you are a bit wrong. There are a number of them, like Nokia SR Linux, Arista CUS, Juniper CRPD, Cumulus VX, FRR, and a few other under the Linux Foundation umbrella. So by moving away from VMs to containers, we give first-class citizen to those things, and that's really nice. what do we gain as well is that we can now be quite light and fast to deploy the labs, right? If you work with containerized network operating system, it is really lightweight, far more lightweight than the VM. For example, an 8-node Claw fabric can fit in a 2 vCPU and 8 gigabytes of RAM VM. That's like peanuts compared to what, for example, XRV wants to have for a single instance. Also, when you use containers to spin up labs, you kind of get or inherit all the familiar features from the Docker. You can use file bins, you can use port exposure, you can create CMD commands, you can propagate environment variables. All those IT workload things that we all know how they work, they will be available for you for your networking labs. And the thing that I love most about it is that the networking lab become really Git friendly. You can create your topology, you can check it out to Git. Somebody can pull it and create this topology right away without really going into the weeds of the UI. Also, when you work with containers, you work with container images, right? So now you can forget pushing your QCOW images to OneDrive or Dropbox. You can push them to the container registry. You can tag them with a version. Somebody else can push it, can pull it or download if they have credentials for the private repo, or you can push it to a public container registry and they will be able to pull it from there. And that is really convenient to share the images that you can build. And the last part, which is quite important, is that now you can run your labs in CI/CD pipelines which are interacting with networking. So what most of the people do with tools like EventG or GNS3, they have it in a private runner in a data center of some sorts, and then they create a pipeline that talks to this EventG server to test things. With Containerlab approach, you can spin up your networking lab pretty much the same way as you do with your IT workload. You create a topology, you spin it up in a private or a shared runner in the cloud, and you test your code or your feature against it. And that is where Containerlab comes into picture. With all those benefits of containers in networking labs, we decided to build a tool that provides a CLI for setting up labs with container-based nodes, right? So you can create quite complex labs, like on the left-hand side, like 3 or 5-stage Claw topology, or you can do just some lightweight labs, like 2 nodes connected together, or 3 nodes or 4 nodes, whatever you need, and then you can spin it up in a matter of seconds and start playing with it on your laptop or your virtual machine or a server. At this point, I wanted everybody to know that there is a huge documentation portal for Containerlab, and it's down below, containerlab.srlinux.dev. If you go there, you will have the documentation portal presented for you, and it answers most of the questions that you might have at this point. But to give you a quick introduction of Containerlab, I would like to get you on a journey. So we'll have 6 steps journey right now. We'll first see how we can install Containerlab. Then we will get to know what is this topology file that I'm talking about, how does it look like. We will deploy a lab, and then we will manage the nodes that will be deployed. We will access and configure the networking nodes that will be part of this lab. We will work with configuration persistency to see how we can save configuration and we can boot with it. And then we will package and push it to a Git repository so everybody else can pull it and reproduce the steps. The lab that I chose for this talk is really simple. It's a 3-node lab. It demonstrates a route reflection capability of CUS, Arista CUS in this example. It consists of 3 nodes. GoBGP, a Linux container, will emit a route towards the Arista CUS. Arista will reflect this route towards Nokia SRLinux, and Nokia SRLinux will have this route in its routing table. On the left-hand side, you see the timeline of the events and the addressing that I will use in this lab, but this is just like for your information. So, installation, step number 1. We thought that Containerlab needs to be really easy to install. Otherwise, it's really hard to get anyone interested in that. And installation of Containerlab is really just one single command, which is highlighted in blue here. You can install it on Windows under VSL2, on Linux, and on macOS with some limitations of the Docker desktop. So you only need to have a Docker installed. No prerequisites, no third-party tools. It's all a single binary that has all the things embedded. So when it's installed, and it's only like 3 seconds, you can get to the actual lab. And the way Containerlab works is that it takes a lab topology file, which is expressed with YAML syntax, and creates those nodes and wires between them. And this Containerlab file, we also refer to it sometimes as a topology definition file. It's really a simple thing. So when we want to create a topology, we start with giving this lab a name. And for our case, the name would be RR, which is short for route reflection. The lab will have a topology, right? That's the third line in this example. And then topology consists of nodes and the links. So right now, I want to create just a single node, or this example just shows a single node. The node has a name, and that is the SR-Linux in my case. The name is just really a string. It's an arbitrary string. You can name your nodes whatever you want. It is the way to tell one node from the other. Then the node must have a kind. And kind is actually what makes Containerlab to understand how to spin this node. Is it a COS container? Is it VMX? Is it CRPD? Is it something else? With kind, you set the expectations, like what this node really is. And the third thing is the image. Containerlab works with containers, so you need to have a container image on your system or pullable from a public container registry. In our case, SR-Linux is publicly available on GitHub Container Registry, so I can use this name here, and it will pull it for me. OK, this was one node. What do we need to do to create those three nodes with GoBGP, COS, and SR-Linux? Well, not really much. We just create two more nodes. You see that on the SR-Linux, there is COS node, and the last one is GoBGP node. Right now, with this topology, like you see on the left-hand side, we will have three nodes deployed, but no links between them. Now it's time to add those links. To add those links, all it takes is just 3 lines. You have links section in the YAML file where you say, my endpoints are, and I'm not sure why the markings are off, but yeah. So the endpoints say, the first one say, I want to connect SR-Linux interface E1-1 to COS node interface ETH1. And you see this will be the link between those two interfaces. You just refer to the name of the node and to the interface that this container will have. It's as simple as that. It's really no magic here. But then you will have your nodes interconnected with VHH pairs between them. And VHH pairs will mean that you have clean data path between the nodes. No bridges, nothing. It's like as pure as it gets. And then when this topology file is ready, you can deploy your topology. You can use Containerlab deploy-t for topology and the name of the topology file. And 30 seconds later, you will have your lab already ready for you. It will consume only 1 vCPU and 2 vCPU and probably 2 gigabytes of RAM for all those 3 nodes. And that's it, right? It's as easy as that. Now when this lab is running and you have this Containerlab summary table with connection information, I wanted to show you how you can connect to those containers, right? These are containers, so we can use typical exec process of the containers. We can say, I want to execute srcli process in the container with the name clab-rr-srlinux. And that's how you get CLI access. Of course, you can also connect to the SSH server. Network operating systems run SSH inside, and containerized NASAs are no different. There is an SSH server inside. So you can say SSH admin at and either container name or the IP address that Containerlab assigned to it, and you will have your shell. And we will have a live demo of that, so don't worry if it's a bit unclear. So now when the nodes are ready, how do we configure them? Well, if you can connect to the CLI, the first and obvious choice is just to dab on the keyboard and something good will come out. But you can also use GNMI, JSON RPC, netconf, eAPI, whatever you have on the nodes. We try to have it already configured for you when you start the lab. So most of the network or most of the programmable interfaces will be available once you start the lab. You can also use config mounts, so you can bind a file from the host to the container, and you will have your configuration used as a startup file, and the node will start with that. Of course, you can use third-party configuration management tools because your containers, they have IP addresses. You can use Scraply, Ansible, Nordenir, what have you, to configure the nodes. And create the use case on the topology that you deployed. And soon we will have a configuration engine backed into Containerlab that will work with labels and variables that you supply to the nodes, and it will create meaningful configurations for you across multi-vendor nodes that we support. Now, the important thing is that Containerlab keeps some state. When you create a lab, and we talk about the lab with 3 nodes, Containerlab will create a lab directory. And this lab directory will have directories per node. So we have SR-Linux directory, we have CUS directory, and we have some certificate directory that we use internally. In those directories, you will find configuration that, for instance, Arista uses and Nokia SR-Linux uses to keep the startup configuration persistent. So that means that whenever you save your changes over the CLI, you will have them immediately available on your host machine. And that is very important because what you can do is that you can create a topology, you can deb your commands on the CLI, and then you can issue a command containerlab save, and it will save the configuration, the running config, to the startup across all the nodes that you have. It's like a bulk save command, so when you're ready, you save it, and it will persist on your disk. So next time you spin up a lab, you can continue from the point where you left. All right, now the lab that I will show you in a demo, the same lab with route reflection capabilities, that's exactly the thing that I did. I configured BGP on SR-Linux, on CUS, I created GoBGP YAML file so that everything is ready for you to see how it works. But then to make my SR-Linux and CUS node to boot with this configuration, I use a specific command, which is called startup config. That's in the topology example on the left-hand side. And I specify a path to that startup config. That's how easy it is to really make a topology that is already pre-configured for a certain use case. And then I packaged it, I pushed it to this GitHub repository, which you see on the top. And now the demo will be like you or somebody else pull it from this repository and see how we can build it. So there goes the demo. Let me. Will it run? Let's see. No, it's on YouTube. Okay, activate. I think that's the thing. No, maybe not. There must be like enable content or something.
Do you have the link on
YouTube?
Yeah.
Yes, I can try. It's harder than it should.
We didn't do it on purpose.
You tell. Okay. Yep, we're back in the game. So I will start with the roots. We start with the installation. So on this containerlab.srlinux.dev, we go to the installation tab. We copy this command, and we paste it to the node. This is just a VM, right? It has only Docker installed, nothing else. We paste this command over, and 3 seconds later, we will have Containerlab installed. Now I go to this topology, to this GitHub repository where I have topology pushed. And I copy the repository URL, and I will clone this to this node where I just installed Containerlab over. And this will get me to a repository, so I can open the directory. And let's explore what I have here. So I have the topology file, that's rr.clab.yaml. This topology file has 3 nodes, SR-Linux, CUS, GoBGP. You see that I use startup config instruction to actually boot up with a predefined configuration that I created manually before. And I also use the images for SR-Linux and CUS. So here I show that my current Docker image store has SR-Linux and CUS images pre-pulled already. And now when I deploy this, Containerlab will pull the missing image for the Go BGP part because I didn't have it pulled before. And then it will start creating the lab. So the numbers on the left-hand side, it's actually seconds since the start time. So as you see, 37 seconds later, and that is because we're waiting on CUS to actually boot, we have this summary table. So now we have 3 nodes, CUS, Go BGP, SR Linux deployed. We have some IP addressing on these management interfaces. And I will connect to SR Linux CLI. You see right now I use the SSH connection, but I could use exec property. Now when I connect to the SR Linux CLI, what I will do is that I will watch if I received any routes yet, because that's the end game, right? We want to receive the route that Go BGP will inject. So I use this BGP neighbor, blah, 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 received routes, IPv4 address family, and SR Linux tells me there's nothing yet. It's like an empty table. I will install the watch over these commands, so the SR Linux will update me every 2 seconds if it has anything received from this peer. And now I will go to the Go BGP part. So on purpose, I didn't make Go BGP immediately send the route because I wanted you to see how it works. So inside the Go BGP, there is a script, Go BGP shell, which calls a few scripts. First is configures the IP address on the Linux container, and then we start the Go BGP daemon, and we made the IPv4 announcement with the last part. It's all on the repo. It's like 5 lines of Go BGP commands, and that's it. So now we can execute this thing, and the way we do it is we use the Docker CLI here. We have Docker exec, container name, and we call this shell script. Go BGP starts, we wait 5 seconds for it to chill, and then we announce the IPv4 route. Now, immediately when I switch back to SR Linux, I see that now my route is there. This 192.168.101 is already received from the CUS. So CUS reflected it to me. If I go to CUS right now, and I can do the same thing with SSH, I can SSH to the CUS container, admin's default credentials, so all good. I can use show IP BGP command here, and I see exactly that I have this route, 192.168.100. I received it from Go BGP. I reflected it back to SR Linux. So that is the Containerlab in action. So now if I go back to presentation, oh, yeah, let me take the other slides right away. So I will start. So that was cool, right? But we do not only work with SR Linux and CUS. We have 9 different vendors, and across these vendors we have 15 different network operating systems. The breakdown between the containerized and virtual machine packaging is currently at 60-40 rate. So 60% of the supported vendor images are VM packaged. But you see that the number of network operating systems in container packages is really astounding. It's 40%. That's a lot. Across the board, we have these vendors already supported with different images. And you see here with these kind strings what we support. So for Juniper, CRPD, VMX, Arista, CUS, both container and VM based, XRv9K for Cisco, Sonic, FRR, and CVX from NVIDIA. Now, I will finish this off with saying that Containerlab is not something that substitutes FNG. It's more like it's a different view on the networking labs. So if you are more on the DevOps side of things, if you work with Git, if you are familiar with Docker CLI, if you kind of like the idea of making your topology Git pushable, then Containerlab might be a great fit for you. Also, if you work with containerized network operating systems, it probably must be the good fit for you. Because not only it has first-class support for containerized network operating systems, it also makes the data path really transparent. So you can have MC lags with LACP, everything is working, nothing is blocked, because it's just a VETH pair. And it's Git friendly. You push your images and your code, which is a topology, to Git, and you manage it with pull requests. You can review stuff. You can do all the nice stuff that you do with Git. That also makes the lab builds pretty much repeatable. You pull the image, you have your topology. There is no way it can go wrong. It will always boot with with the expected configuration. The footprint is rather small, and you can deploy the labs really fast. Now, it's not everything is green and shiny, right? There are fewer traditional NOSes that we support in Containerlab. Like in EVNG, you have probably 100 already, or whatever the number is. In Containerlab, we have just like the most critical ones supported. And there is no UI, so if you want to drag and drop, click and deploy, it's not something that we currently have. So if that sounds interesting, the way to do the next steps probably would be to explore the documentation side. It has a lot of things inside it. Containerlab is not just for 3 nodes topologies. You can build telemetry labs with Grafana and Telegraph and whatever, and they will be quite huge, and they will still be lightning fast to deploy. So you can try to create a lab with your network operating system of choice. If something is not right, or you want to propose an idea, GitHub issues or GitHub discussions is the way to go. And you can also join our Discord community. The link is in the documentation side. And yeah, if you liked it, give us a star on the repository. That would be really great. And with that, I finished. Thank you very much for listening. Taking questions?
Are there, yeah, thanks. I see there's one question. Go ahead.
Hello, Andrei from RipeNCC. Thank you. It was a very interesting presentation. I wonder how open are actually those containers network operating system? For instance, can I just grab the image of the network operating system and redistribute it as a part of my product? Or is this problem, does everybody have to download their own version of the container or something like that?
Well, if you have your network operating system in a container package, then Containerlab can work with that already. There is no integration effort really, so there is no proprietary containers or something like that.
You don't have to like agree to EULA to download it or something like that.
Sorry?
Like in end-user license agreement, you don't have to agree. It's
well, as a Containerlab user, you are responsible for images, so you need to bring your images with you, right? Containerlab comes without any images, so you have to have them on your machine or pull it from somewhere.
And do you know how hard it is to get them?
That's a great question. Yeah, so for example, like if you take Nokia for Linux, you can pull it just right now. There is no strings attached, no licensing, nothing. If there is Arista COS, for example, then you need to have an account with the Arista side, but it's free. So you just register, you pull the tar archive, and you load it. Some other systems might be more restrictive, so you might have to have a license, for instance, to use them. But so far, none of them really require it.
All right, thank you very much.
Yep.
There's also a question via IRC.
Yes, there is. It's a question from Gordon. The question is, let me look. Containerized network operating systems, as far as you can tell, mostly contain the control plane of the NOS they're derived from. So do you have any recommendations or insights or pitfalls for modeling logical physical networks on a large scale? For example, testing a candidate config for an entire network and not just verifying that the generated config is correct.
Well, I think the containerized network operating systems, so that they are upcoming. It's not like you can have XRV, for instance, in a container. You would still need to use a VM. But if you work with containerized SR Linux or COS, you can have full feature parity with the virtual offering of the same system. So you can spin up a topology as big as you want, and you can test the data path, the control plane, the management plane, as much as the operating system supports.
I'll try to summarize the discussion we had on IRC just now about that, because some people remark that it's sometimes hard to model like switches with 48 or 96 or more ports in a virtual container.
Well, it's a limitation of the virtual image and not the tool.
I understand. Thanks.